Hi, today I'm here to talk about our project for CS4910 on WPA standards. In this project, we explored the history of WPA and the different versions and compared their performances and the vulnerabilities that they have, as well as explored how they're still used and distributed and which ones are most used in a real world setting. Our project objectives since the proposal changed somewhat. And originally we had been planning on testing both the vulnerabilities of WPA as well as more frequency jamming aspects. However, due to cost and other issues, we decided to focus mainly on the encryption side. And so our final objectives for this project changed slightly so that we would record and examine communications between the different types of the standards. We tested for any performance trade-offs. We looked at and implemented a weakness in the older version via de-authentication attacks. And then we also did a war driving experiment where we went around and recorded networks and which versions they were using to see which ones are most prevalent and if there has been any serious upgrade to WPA3 yet as it currently stands.
When we start looking at Wi-Fi, we understand that we need it because a multitude of reasons. We need it because of space, we need it because of physical constraints, we need it because of hardware limitations. But when we start looking at that, we understand that there are limitations of itself. We use Wi-Fi for a multitude of reasons. We use them for our home security systems when they're connected to a Wi-Fi network. An example of that would be like ADT uses a telephone receiver system that actually connects through your Wi-Fi, transmits out. You use it for home automation systems such as your lights or your heating and air. People use them for their tablets, laptops, some phones. And typically, and as it relates to this presentation, we're going to focus on 2.5 gig or the lower band of Wi-Fi signals. And the reason why we're doing this is twofold. For one, the typical system uses the 2.5 as a preference over the 5G network, simply because 5G network is very power restrictive or has a very limited range because of the power that's used for it. And you're exposed to Wi-Fi not only in the home system, but you also see it like Starbucks, you know, that guy that's mooching the Wi-Fi all day long, internet cafes, that kind of thing. You'll see it in airports. And there's a multitude of systems, as I said, that use it, such as like, you know, the Internet of Things or the IoT devices. So when you're dealing with your Wi-Fi systems, you're constrained by two different things, right? You have your hardware side of the house, which is your Wi-Fi router, your modem, or your direct connection to the ISP via the satellite or, you know, DSL hookup, that kind of thing. And there's typically not much in the way of hardware limitations other than, yeah, that's about it. As far as your software side of the house, you are limited on how many systems you can connect to your network. It's typically for like a Class C network, somewhere in the tune of like 250 to 254, depending on your loopbacks and your network divisions, that kind of thing. So there's something called a deauthorization request, and what happens is it's kind of like your keep alive request, where, you know, the router's like, hey, do I still need to allocate a particular IP address for like DHCP networks and stuff like that. So they're gonna send out this request to each one of the nodes or each one of the clients on the network, and it's used to basically prevent overcrowding of networks. All right, it's a very normal, it's a routine procedure, that kind of thing, right? And it's used to remove idle systems from an overcrowded network, such as like the internet cafes or like Starbucks. There's a bunch of people mooching off of the network. And it's used from the access point to the client, and from the client back to the access point. In the case where somebody's leaving to go from Starbucks to the internet cafe across the street. So they're leaving the network, and they close down their network, and they shut off or they disconnect, and that sends back a deauthorization request back to the access point, and lets them know, hey, you can reallocate my IP somewhere else, or you can use it however you want to do it. Normally, in the process of authentication, this deauthorization request occurs, or the execution happens during the stages 3 to 1 in this diagram on the slide. And what essentially happens is during the third to first authentication request, that deauthorization or deauthentication notification is happening, and the access point says, okay, got it, right, we're moving you. Now that we know what a deauthorization request is, let's see what a deauthorization attack is. Essentially, a deauthorization attack is a denial of service. It's a targeted attack against a user and a Wi-Fi access point. The deauthorization attack is typically the precursor for an additional attack, or a more robust attack, right? It's used to disconnect the user in an effort to capture the authentication handshake during the reconnection, or the repeated, like, hey, what's going on? One of those things. Why did I get disconnected? Why is it saying I need a? It's used to capture that information that you're about to transmit. And typically, the deauthorization attack is followed on, or it's a precursor to, like a dictionary or a brute force attack, where somebody's going to go through and just capture your information, decipher what your password is, use your information to basically authenticate themselves somewhere else. And yeah, it's not good. So when we started approaching the deauthorization attacks, we started looking at the various different hardware, or the software, whether it was SDRs or hardwares, creating our own little barrage jammer, like a Jacob's ladder or something like that. We started understanding that the equipment can get very, very robust, very, very big, and really create a lot of issues when it comes down to spacing, power, time like that. So we started looking at, hey, SDR. We started looking at that. Basically, we came up to not necessarily an SDR-driven device, but more of a total piece of of equipment that you can employ without needing a lot of stuff. And we came up with the ESP8266 microcontroller, right? What this is it's a Wi-Fi enabled microcontroller that uses, that operates in an unlicensed frequency range between 2400 and 2484 megahertz, right? And this is the 2.5 gig network, right? It was under $10, and it transmits on the IEEE 802.11b, and N network standards, right? Now it's a short range due to its size and limited powers. I mean, this is like a little, USB device that you hook up with your normal micro USB and hook it up to a 9-volt battery, and you can put it up probably to a couple AA's and just set it out, program it. It's already live, right? It's programmable to be a packet sniffer, to send deauthorization attacks, and to do beacon attacks. So it was pretty compact, pretty capable, right? We were able to find software that was on GitHub, and that came with like baseline deauthorization software, which is readily available. So, as I mentioned, the ESP8266 operates on the 2.5 gigahertz range. And what that is it's the ISM band that was established by the FCC back in the mid 80s, I want to say 1985. And what that did is that chunked up, or it broke down the frequency range from 2400 megahertz to 2484 megahertz. And that allowed the breakout of approximately 14 different channels to be utilized as your Wi-Fi channels. So as we look at the evolution of the 802.11 standards, right, we can understand that we've changed from the B to the G to the N, and at some points the A and the AX networks, right? We start to understand that as technology has changed, so have our capabilities. So from the first part of it, when you're looking at the B networks, right, you're dealing with the DSSS, which is the direct sequence spread spectrum, and that used the main core non-overlapping channels within the frequency range, right? And it gave them about a 22 megahertz span per channel to transmit on. I mean, they were able to transmit across, but as you're starting to gate off, or as you're starting to set up your Wi-Fi network and you're limiting to the certain channels, it uses a 22 megahertz range. Right? Then as it evolved, then you have the OD or OFDM network, which is the orthogonal frequency division multiplexing, and they changed it from a 22 megahertz range to a 16 and a quarter megahertz range, right? And that was used by some of the subcarriers, right? That changed from the B to the G and N networks, right? And here is a depiction of how it's treated. Right? And what that does is it allows compression, it allows for phase shifting, and it allows for a little bit better transmission distance and range and capabilities of what you can pack on top of it. And it's harder to unfold it when you're looking at trying to decipher frequency-wise, right? When you're talking about trying to decode ones and zeros, a little bit different than trying to decode or trying to break out frequencies, right? And that also goes in with the N network, and it's just more of an expansion on the OFDM networks, and that expanded it up from the 16 and a quarter or 16.25 to the 40 megahertz with a 33 and 3/4 megahertz sub-channel carrier, sub-carrier frequencies. So basically it allowed, as technology has changed, it's allowed us to change up the types of channels and allow for cleaner transmission throughout the network.
This was our test network setup for our performance tests. As you can see in the middle, we have a small little Raspberry Pi that ran as our server. It was running Debian and had an iPerf3 server so that the client could communicate with it and transfer information back and forth. That's attached via an Ethernet cord to a Archer TP-Link router, which could be set to communicate either WPA, WPA2, or WPA3. And on the right, we just have a basic laptop running Ubuntu that was the client and communicated wirelessly through the router to the Raspberry Pi server. This slide shows what the iPerf3 software looked like. As you can see from the image, it would run and give us an analysis of the transfer rate in kilobytes per second of the sender and the receiver, as well as how many packets needed to be retried. For our test, we ran 60-second tests 10 times for each of the 3 standards to try and get a good average of how each one was performing. This slide shows the results from our performance testing. As you can see from the graph, there were no real significant changes between the performance of any of the standards. There was a small dip for WPA2, which possibly could be from experimental error or from maybe slightly less efficient encryption, but we needed to do more testing to confirm. But I think the real takeaway from this data is that even though WPA3 has believed to be the strongest security protocol, there is really no trade-off as far as it goes the transfer rates. after doing the performance test, we wanted to show a weakness in the older versions of WPA, and so we did a de-authentication attack on our performance network. We used the ESP8222 chip and attacked our private network called Death Star. And we were able to try and tag it with each of the different standards by changing the settings in the router. And for this, we started with a base coding program available on GitHub that we've attached in our report appendix. And I'm just showing on the right a couple of the more important coding sections that we tweaked to specifically only attack our private network for ethical reasons, and to specifically only do the attack on our one device. This slide shows the results from our de-authentication attacks. As you can see on the table, WPA and WPA2 were successfully attacked, whereas WPA3 was not susceptible to the attack. And the picture on the left shows what the user would see if the attack was successful. Essentially, they would be kicked off of the network. As we saw, the performance of WPA3 was comparable to the others and seems to have a better security enhancement. And so, with it being announced in 2018, our final question of the project was, is it common, and which standards are most common currently at this time? To answer this question, our first plan was to reprogram our microchip to be a mobile Wi-Fi network scanner. However, the hardware supported it, but the Arduino software libraries for the chip did not. And so we just didn't have the time or resources to build new libraries for the device. And so instead, we decided to take our Ubuntu laptop and write a shell script that could scan for nearby networks. And we wrote this original code by ourselves and recorded the MAC addresses and the standards that the MAC address was using to make sure we weren't doubling up on any networks, and also were able to record which networks were being used in real life. This is the code that we wrote for the network scanner script on Linux. It runs a command that goes and scans for any network and then grabs the Wi-Fi standard that it uses, and then it just does some text parsing and puts the MAC address and the version into a file that you specify. As far as how we implemented the rest of the experiment, as I mentioned before, we did some driving. We picked 3 different types of locations: a residential neighborhood, a shopping center, and UCCS campus. And we went to each of these locations and then found 5 sub-locations in each place where we scanned the networks, where we believed that there would be a series of networks to test and see what standard they were using. We found that WPA2 is by far the most prevalently used network currently. In all 3 locations, it was the most prevalent. We were surprised by the fact that there was still quite a bit of original WPA use around and almost no WPA3. The only WPA3 we found were in residential areas, where our hypothesis is that there were some security-minded individuals that had set up their own networks specifically for being as secure as possible. In conclusion, our project shows that there have been significant improvements in the security of WPA standards over time, which haven't really come at serious performance costs. Yet, WPA3, the most recent one, isn't very prevalent, probably due to cost of installation, lack of awareness, and no mainstream, really well-known security issues with WPA2 that the public knows about and would be inspired to upgrade. And therefore, it brings to discussion how soon we need to push for WPA3 and whether WPA2 is a valid security standard for the foreseeable future. Here's a short list of our references for both the presentation and the report. And that's everything we have for you. Thank you for watching our presentation, and if you'd like to contact us, we can be reached at either of the emails at this slide.